fast recap before we add more tools to our toolbox, okay? Geometric, what else have we done? Alternating is what we did last time. P-series, telescoping. Nth term test, and one more, integral test. All right, so we're going to add 2 more tests to our toolbox. These are both comparison tests. All right, the first one is a limit comparison. And first of all, before I start this is something that's obvious to me, but I have to remember to say it to all of you. You want to pick a series to compare to that is usually a P-series, because those are very easy to determine whether they converge or diverge. P-series and geometric. The idea when you're doing a comparison is you're taking something that's sort of complicated and you're comparing it to something that's easier. Make sense? Kind of like, when you do a U substitution, you take something that looks really complicated and then you make it look a whole lot simpler. So if you do limit as n goes to infinity of the 2 series, and it really doesn't matter which one goes in the numerator and which one goes in the denominator, because stuff's going to cancel out anyway, and you'll see. But usually I put the original one on the top and then the one I compared it to underneath. But again, you can reciprocate. It doesn't matter. Bless you. If that limit is positive and finite, which finite means what? Yeah, not infinite. So not infinity. So if you get an answer, essentially, then both series do the same thing. They agree with each other, like the one you compared it to. So if that is true, both converge or both diverge. So essentially you're saying, hey, this one's really complicated. So instead, I'm going to compare it to this much simpler one. And whatever that one does, the original one does too. Okay? So looking at this, we're going to compare to another series, and basically you just get rid of all the complicated part, or you take like who's in charge here, right? So I'm going to compare it to this one. I just got rid of that +1 essentially. And then I'm going to simplify my exponents. A square root is n to what power? That's 1/2. And then down here I have n squared. So if you do 2 minus 1/2, you're going to get what? I'm going to simplify it together. Yeah, here, let me do a margin problem. It looks like this right now. So it's going to be 1 over n to the what? You want to subtract these. 2 minus 1/2, so 3/2. Or 1 and 1/2, but typically you would see it as 3/2. Now that's a P-series. So we compared it to something that we can tell whether it converges or diverges fairly easily. Is P bigger or smaller than 1 here? Bigger, which means converges. You got a while until the test. This is a long unit. They are opposite of each other. So, okay. But by test day, you'll have to have that sorted out. All right. So converges because P equals 3/2, which is bigger than 1. So what we're going to try and say is, since that one converges, the original one converges too. And the way you prove that is with this limit. So we're going to do limit as n goes to infinity. And again, it kind of doesn't matter. I usually put the original one on top and then the one I compared it to in the denominator. So I'm going to recopy this and then put that over the one that I compared it to, which is this one that I'm pointing at right here. It looks really awful, but only for a second. Some things are going to cancel. When you divide by a fraction, you multiply by the reciprocal. So I'm going to multiply and then flip this over. And I know I wrote that really fast. I tried to write it fast so you could see it and copy it down. But what's going to cancel or divide out? Yeah, the square roots of n are gone. I have an n squared in the numerator and an n squared in the denominator. So since that's a tie, we're going to use coefficients, which are both 1. And so this whole limit comes out to be 1, which is positive and finite. It is positive and finite. So what we get to say is, since the one we compared to converges, this original one also converges. So we're going to say converges by limit comparison. What I'm going to do, since we're short on time, is I will work this one out and post a picture of the solution to Schoology if you're interested in it. But that second one goes a lot like the first one. Is that fair? Like I want to be able to finish it. Okay, but we are going to do question 3. I'll work this out and I'll post, you know how I always post a link to the video, like when I'm recording? I'll put like another link next to it and I'll work it out by hand and then you can have a picture of it if you're interested. All right, so we're going to do a comparison. So let's think about what we want to compare to. You kind of just want to get rid of all the fluff or sort of take who's in charge here. So for the numerator, who's in charge, the n or the 2 to the n? Like which one is more influential, so to speak? Yeah, the 2 to the n, the exponential part. And in the denominator, it would be, yeah, and you don't even need the 4. It's really just who's in charge here. So I'm going to do an nth term test with that. It's not a p-series. It's not geometric. So I don't have one of those simple ones that I can compare it to. So I'm going to do an nth term test. The numerator is exponential. The denominator is polynomial. Exponential grows faster than polynomial. So this is going to go to infinity. Perfect. So we're going to say diverges by nth term test. And so what our goal now is, we're going to try and say the original one also diverges. Again, it's like you're saying, I'm going to compare to this other thing, sort of like a straw man argument, kind of like you're saying, I'm going to compare to this other thing and then go, well, because, do you get what I'm saying though? It's because that one did this, then this one's also going to do the same thing. Okay. So we're going to do limit as n goes to infinity. We're going to take the original one over the one we compared it to. And again, that is going to look awful for a second and a half. Like you just have to get through writing it. But then stuff is going to cancel and it's not going to be that horrible. So limit n goes to infinity. I'm going to recopy this first one. And then you multiply by the reciprocal. And something should go away. Usually that's what's going to happen, is something should divide out. So what in this case can I cross out here? Yeah, 2 to the n. Now that means in the numerator you have n times, did I write something wrong there? Hold on, did I do a copy error? Yeah, but that's not going to go. You know what? I messed this one up. Because that's not positive and finite. Can I recheck? I messed something up in this, and we don't have time right now. Can I get back to you on that one? Very sorry. I try to be very perfect for you guys at this level, but I messed something up. Let me take a minute and dig through that, but I messed something up on that one. I'm so sorry. Yeah, I will get back to you on it. I'm so sorry. Can you accept that as my answer for right now? I'm gonna dig deeper into it and figure out what I messed up on that problem, and I'll get back to you. Yes. For the moment, yes, because we only have 15 minutes, and I'm trying to get through this. Pretend for one. Can you pretend for me though? Do you all have an imagination? Pretend this came out to something positive and finite. Then we would say diverges by limit comparison. We would say since this one diverges, the other one diverges. It was supposed to come out to something positive and finite, and I thought it did. I messed something up, so I'm really sorry. I will figure out what I messed up about that, and I'll get back to you. All right, that was limit comparison. So if you do that limit and it comes out to something positive and finite, you get to say, well, they have similar behavior. The other one is a direct comparison. Now, for this one, you need to know which series is smaller than the other one. So you're comparing them. It is a direct comparison. So there's going to be two if-then statements here. If B sub n converges, then A sub n also converges. And I'm going to write out both statements and then we'll talk about them. Let me get the writing done first. So if B converges, then A also converges. If A diverges, then B also diverges. So take a minute and write it down, and then we'll just have a brief conversation on why that's true. The example I always use is, do you know, like at an amusement park, it's like you have to be this tall to ride the ride? Okay, so if the taller person, where am I at? B? If B is the taller person, are we coming with me on this like analogy here? All right, if B is the taller one, if B is not tall enough, like if B is underneath that height, then the shorter one is obviously also like below, like too short, but that means they're going to converge. It's like small enough. If the shorter person is too tall, like diverges means it gets too big, right? If the shorter person is too big, then obviously the taller one is also too big. Does that example make sense? Yeah. Or however it sorts out in your mind, or if you just want to flat out memorize this, we'll just do two of these as well. We'll do 4 and 5, right? So we're going to do a comparison. We're going to compare to, and what would be a good series to compare to? Just get rid of the fluff. 1 over n squared. And the reason that's a good one is that's what kind of series? P series. Because named all of them, so that's good. P series. P is 2 and is greater than 1. So we're going to say converges because P equals 2, which is bigger than 1. And our goal now is to say, since that one converged, the original one does too. All right, so if that one converges, we need to say that this original one is bigger or smaller? Smaller. So we need to say that this one is smaller than the one we compared to. Because we're saying if this one converges, like it's too short, then the one smaller than that will be as well. So now, is that true? Is this going to be smaller than this? Yes. And usually we say 4n bigger than 1. If you try to plug in 1 and that doesn't make the statement true, try 2 or try 3 or try 4. Usually eventually it'll end up being true. And you can say for n bigger than 3 or however far it takes you. Do you get what I'm saying? Like if 1 doesn't work. So we're going to say, what's our big conclusion to the whole thing? Converges by direct comparison. Well, it depends on if you're saying converges or diverges.
And direct comparison is not using limits.
Correct. Limit comparison is with the limit direct. So there's something to be said about each of them. Like, I like the limit one better. That comes out positive and finite. You get to say these are the same. Some people don't like limits, but here you need to fiddle with which one's bigger than the other one. Actually, no, I just changed my mind. We're going to do 6 instead. All right, so we're going to compare to. Now, it feels like you should compare to what? 1 over square root of n. We're actually going to compare to just 1 over n. I don't have time to take you through the whole thing, but if you do it that way, the which one is bigger than or smaller than the other one won't work out the way that you want it to. You'll come out to a dead end and you'll be like, oh, whoops. I made the split decision to talk about this one because you mentioned what this one is. So I wanted to talk about it. What is this? It's your harmonic series. Or you could say it's a P series where P is 1, but either way, it diverges. So you can either say diverges because P equals 1, which is less than or equal to 1, or you can say diverges because harmonic series. That one comes up a lot. So saying that counts as a justification. It's sort of by definition.
I thought harmonic series converged to, or some of two. No?
Mm-mm. It is in the notes, but I'll go back and find it.
Okay.
But diverges because P is 1, which is less than or equal to 1. Remember, for geometric and P series, the equal to goes with the divergent version of it. They're opposites of each other, but the equal to, if either of them equals 1, that's diverges.
Okay.
For geometric and P series. So now what our goal is to say, since this one diverges, that one does too. So we want to say that 1 over n is the smaller one. Does that make sense? Because if this one diverges, like if this one is too tall to get on the ride and this one's bigger, then it's going to diverge too. Now, I'm pretty sure this doesn't work for 1. Humor me for a second because I'm pretty sure it doesn't. If you plug in 1, this side would just be 1. This would be 1/3. Is 1 smaller than 1/3? No. I'm pretty sure you have to go all the way out to 4 because that's where the square root turns out nice. If you plug in 4, this would be 1/4. And then what would this be? 1/4. Good. And then if you go beyond, it's going to work. Like if you try plugging in, try plugging in 9 because that's the next perfect square. You would get 1/9 is smaller than 1/5, which is true. Okay. So what's our big conclusion to the whole thing? Yeah, diverges by direct comparison. So here's what I'm going to do. I'm going to fill in number 2 and number 5 that we skipped. I'll take a picture and I'll post them along with this video. And I will, while you're working on your classwork, go back and try and figure out what I messed up on number 3. I just made an error in the problem. The problem did not work out. Does that make sense? Like we didn't do anything wrong. The error was, I built a poor problem. You know how I always say that on the AP exam, they're not going to give you an undoable problem? I kind of accidentally did that, so I'm sorry. Oopsie. I'll figure out what I messed up and I'll fix it for next time.